Bifrost Graph is a powerful new procedural content creation framework from Autodesk. The Bifrost Extension is a free Maya plugin for creating tools to accelerate almost every aspect of 3D production. Using the Bifrost visual programming environment, artists and technical directors in all 3D disciplines can automate complex processes and generate assets without writing a single line of code. My name is Aaron F. Ross, and I'm excited to present this course on the basics of the Bifrost extension for Maya. Our learning goal is to get familiar with the Bifrost graph and how it works. I've been waiting for this for years, and I'm super enthusiastic about sharing these amazing new opportunities with you. Let's expand our horizons with the Bifrost extension for Maya. Before launching into Bifrost, let's briefly discuss the course prerequisites, or what you need to know. This is an intermediate course for Maya users. If you have no experience in Maya, you might have difficulty following some of the exercises. If you've got substantial experience in another package, such as 3ds Max, Blender, or Houdini, that can be helpful, but if you've never used Maya, you may get lost. In that case, I recommend taking a look at George Maestry's courses here at LinkedIn Learning, such as Maya 2020 Essential Training. Bifrost is a general tool development framework. As we'll discuss later, Bifrost can apply to nearly any 3D production task, such as modeling and animation. You'll need to be fluent in core 3D concepts like polygon meshes and material shaders. Experience with dynamic simulations and volumetric rendering can help, because those are key features of this first release of the Bifrost extension. Now let's talk about the technical requirements. Some of the exercises in the course are dynamic simulations, and to complete those lessons you'll need a computer that's up to the task. As a general rule, you'll want a fast central processing unit, sufficient random access memory, and lots of hard drive storage space. The CPU should be the equivalent of an Intel Core i5 or better. 16 gigabytes of RAM or more is recommended to prevent slowdowns from virtual memory swapping. We'll be caching a simulation to disk, and that will eat up a considerable amount of hard drive space, about 10 gigabytes. To be on the safe side, you should really have more like 20 gigabytes available. The Bifrost extension is available for Maya 2018, 2019, and 2020. This course is produced in Maya 2020, and the exercise files are saved in that format. But as long as you have Bifrost 2.0.4.0 or later installed, you should be able to open the exercise files in any of those Maya versions. To get the latest version of the Bifrost extension, go to the Autodesk area website. The current web address of the download page is area.autodesk.com/bifrost/downloads. Those are the prerequisites for this course. If you have access to the exercise files I've created for this course, you can go ahead and download those and extract them to a convenient location. I've placed them here on my desktop. If you don't have access to the exercise files, then in some cases you can use your own assets to follow along with the lessons. However, in some cases you may find it difficult to do so because the lesson relies upon a compound or a Bifrost asset that I have provided. And we'll see that in the exercise files. I've got a standard Maya project here, and inside that Maya project I have a custom folder which is labeled Bifrost. Inside there we've got compounds linked in, and then a JSON file of a simplex noise deformer. So if you don't have the exercise files and you don't have this JSON file, then you might not be able to follow some of the exercises. But even so, you can still learn by observation, and that would apply also if you had no access to Maya. For example, if you're on a mobile device or just simply didn't have Maya in front of you at the time. If you are planning to follow along with the exercises, then you'll need a Maya project folder, either this exercise files folder that I provided, or a custom project that you've created for the course. Let's talk about creating a project first. In Maya, we can go to the File menu, to Project Window, and we'll want to create a new project, so we'll click New. and give that a name. We can just call it Bifrost. And we want to place it somewhere, such as in the current user's Documents Maya projects, or maybe on the desktop. We can browse by clicking on the folder button, and I'll just choose Desktop and select. We can leave the rest of this stuff as it is and just click Accept, and that creates the folder. Here it is, Bifrost. We can open that up, and we'll see that we've got a Maya project folder structure with nothing in it yet. If you are going to use the exercise files I've provided, you want to set Maya to that project. Back in the Maya File menu, go to Set Project, and then browse, in this case to the desktop. Select the root level of that folder, in this case exercise files, and click Set. And now if we go to the File menu and choose Open Scene, we're taken to our current project's Scenes folder. And you'll notice that these are tiny, tiny files. Look at this. Each one of these is on the order of 100 kilobytes. We could fit 10 of those on a floppy disk, if you know what a floppy disk is. The reason these are so small is because they are Bifrost files that are merely instructions on how to generate procedural content. These are not heavy polygon meshes or animation with many keyframes. That can take up a lot of space on disk. But as we'll discuss later, these are really just the recipes for creating things and not the things themselves. You'll see that some of these Maya scene files have the words finished example appended to the end. That indicates that the file represents the end state of that particular movie. Usually it's the begin state. So for example, O2 install compound is the begin state for that movie. If there is no finished example, then the end state of that movie is the begin state of the next movie. So in other words, O2, 03 construct graph is the begin state for O2, 03, but it's also the end state for O2, 02. So these follow in kind of a sequence until we reach a finished example, and that's kind of the end of that line. All right, so that's how to set up the exercise files for the course. The Bifrost extension can be described as a visual programming environment. Even if you have no experience or interest in computer programming, don't think that the phrase visual programming is a barrier to entry. The reality is quite the opposite. Bifrost is a great opportunity for everyone, regardless of prior programming experience. One of the primary goals of the Bifrost development team is to make 3D graphics programming more accessible to less technical users. Let's define visual programming and see how it applies to the Bifrost graph and the Maya node graph. A visual programming environment is a graphical user interface that accelerates the process of creating computer code. Instead of a text language, such as C++, MEL, or Python, a visual programming environment uses a graphical language of interconnected blocks of code called nodes. You're probably familiar with node-based interfaces, such as the Maya Node Editor and the Hypershade Material Editor. These are also a limited form of visual programming, inasmuch as they enable us to design algorithmic pathways through which scene data can flow. But the Maya scene graphs operate at a very high level. Effectively, that means users have little or no ability to make changes to the way nodes and attributes operate. Using the Maya interface, we can make connections, change attribute values, add custom attributes, and write scripts to automate functions. But we cannot go inside a Maya node, such as a deformer, and reprogram its behavior. To do that, we'd need to modify the node's source code and recompile it to machine language. But the Maya source code is not publicly available. And even if Maya were open source, modifying its code is beyond the technical abilities of the vast majority of users. But the Bifrost extension blows away all of those limitations. Bifrost ships with a collection of high-level nodes called compounds that we can drill down inside of in order to change their behavior at a lower level. Since Bifrost is a full-blown programming language, it also provides a comprehensive library of base-level nodes, such as mathematical operators. We can construct node graphs of arbitrary complexity from these building blocks. The graph is our source code. And we don't need to worry about compiling that code to machine language. That's all automatic and happens in real time. And that's called just-in-time compilation, or JIT. It's super fast, and in most cases you won't even know it's happening. Even the heaviest, most complex graphs will compile in a matter of seconds. The key characteristic of the Bifrost extension is openness. Consider the Aero solver for volumetric effects such as smoke and fire. Aero comes in two versions: the legacy Bifrost fluids and the Bifrost extension. If we create an Aero effect from the Bifrost fluids menu, we get a couple of Maya shape nodes with fixed pre-programmed features. But if we create an Aero effect within the Bifrost graph editor, we can open up the various nodes of that solver and fundamentally alter them. A Maya node is a precompiled, closed, black box with no access to its inner workings, but the Bifrost graph is an open visual programming environment. Another way to describe the Bifrost extension is as a procedural content creation framework. Let's explore what this means and identify situations where Bifrost is most useful. Content creation encompasses the production processes of making assets, such as models, materials, animation, and renderings. Traditional content creation is mostly manual, crafted by hand. For example, character modeling is generally a manual process of virtual sculpting. Traditional character animation is generally a manual process of keyframing. Content can also be captured from the physical world. We can scan a 3D model of a real person instead of sculpting the model by hand. Likewise, we can capture the motions of a performer to animate a computer-generated character. Procedural content is not created by hand, nor is it captured from the physical world. It's generated by some computer procedure. Now, the term procedure has many meanings, but in this context, it signifies an algorithm or logical process to generate or modify content. That's why it's sometimes called generative instead of procedural content. A procedural algorithm is a set of operations that obey established rules to produce an outcome. It's instructions for how to generate or modify content. A common analogy is that the procedure is like a recipe for a cake. The output, or the resulting final asset, is the baked cake. But unlike real-world baking, with proceduralism, we can actually unbake the cake. A distinguishing characteristic of procedural content is that it is non-destructive and reversible. A procedural algorithm generates assets based on logical rules rather than on manual processes. We can easily change the input values and generate a different result. Then we can set the inputs back to their original values and restore the previous outcome. This is something that is notoriously difficult to do in traditional content creation because many changes are generally destructive and non-reversible. To use the recipe analogy, in traditional content creation, we can't unbake the cake. All we can do is hit the undo button and load the last state from memory, or load a previous saved version from disk. Even when traditional content creation is non-destructive, such as with the Maya construction history, it tends to be slow, difficult to work with, and even unstable. Those are some of the reasons why we need to delete the construction history so often. But Bifrost is built on a much more advanced code base. It's fully procedural, blazing fast, relatively easy to use, and rock solid. Bifrost is a framework for building and using tools to generate procedural content. Think of it as a set of tools for building other tools. Since Bifrost is a comprehensive visual programming environment, there's almost no production process that can't benefit from the power of proceduralism. Bifrost is in its early days, so at this point there are a few key areas where high-level tools have been fully developed. The first full-featured, ready-to-use tool set is the Aero solver for volumetric simulations. Physical simulations are the most obvious application of proceduralism because it's not possible to achieve believable results any other way. Bifrost currently also offers particle systems and a material point method solver for cloth and granular materials such as sand. These solvers are all integrated, meaning that they work together and affect one another, and that is a major step forward for dynamics in Maya. But proceduralism isn't just for simulation, it applies in many other areas. For example, we could use Bifrost to build a system to generate procedural character models. We plug in the desired parameters such as height and body type, and Bifrost does all of the heavy lifting to generate the model. Or we could build a Bifrost graph for procedural animation of motion graphic effects, with many different shapes moving in complex ways that would be too time-consuming to animate by hand. Another common application of proceduralism is scene population, where objects such as trees and buildings are generated and placed in the scene automatically. As I record this course, the 3ds Max software team is hard at work using Bifrost to develop tools for precisely that purpose. So Bifrost is not just for simulation, and it's not just for Maya. It's a whole new world of possibilities. The Bifrost Extension is a plugin for Maya, and soon other applications such as 3ds Max. As we've discussed, Bifrost is a node-based framework or visual programming environment for building and using new and more efficient tools. I'd like to go a bit deeper and talk about how the Bifrost Extension interfaces with Maya. To understand that, we also need to understand a little about the node-based architecture of Maya. It's been decades since the first time I heard the saying known as the Maya mantra. Maya is a network of nodes that are interconnected. That's generally true, but it's a little bit more complicated than that. Maya actually has two separate node graphs, one for transforms and one for everything else. Transforms are the position, rotation, and scale attributes of objects. Any renderable object and almost any non-rendering object has a transform node to place, orient, and size it in the scene. A few other node types, such as groups and skeleton joints, also store transforms. The graph of all transforms in a scene is known as the DAG, or DAG, which stands for Directed Acyclic Graph. It's a type of node graph that doesn't allow circular connections or dependencies. For example, an object cannot be both parent and child to another object. All of the non-transform nodes are in a different scene graph with a very confusingly similar name, the DG. That stands for Dependency Graph. The dependency graph does allow circular dependencies. So, for example, the output of a node can be connected to an input on the same node. The most familiar category of dependency graph nodes is shape nodes, which define the forms of objects. A mesh shape node consists of polygons and various other attributes such as display properties. There are many other categories and types of dependency graph nodes, such as materials, lights, construction history, deformers, and so on. The DAG and the dependency graph can be connected to one another. For example, we can use transforms to drive material attributes. And shape nodes are connected to their respective transform nodes, although that connection is not visible in the Maya interface. But even so, the DAG and the dependency graph are fundamentally two different data structures. The Bifrost extension adds a third node graph to Maya, but it is very different to the DAG and the dependency graph. Bifrost is its own bubble universe inside Maya. Whatever happens in Bifrost stays in Bifrost, unless we connect it to Maya through input and output nodes in the Bifrost graph editor. The Bifrost graph is implemented as a node within the Maya dependency graph, called Bifrost Board. The Bifrost graph appears in the Maya outliner and node editor as if it were a DAG node, but that's just for convenience, and the graph itself is not a 3D object, and it has no transforms. The output of the Bifrost graph is separate from the graph. The output could be a mesh, or a volume, or particles, or who knows what may come in the future. But in any case, the graph output is a node type called Bif shape. Each Bif shape has its own transform node, just like an ordinary Maya shape. But the Bif shape isn't an ordinary Maya shape. It's a completely different animal, and its behavior may defy our expectations. For example, a polygon mesh object output from Bifrost is not a Maya mesh, so it's not compatible with the Maya modeling tools. If you try to apply a Maya mesh command or tool to a Bif shape, nothing will happen except an error message. But don't worry, we can always convert a Bif shape to a Maya mesh shape if needed. Bifrost is developed separately from Maya. That's very good because it means Bifrost breaks free of Maya's limitations in both feature set and performance. A separate Bifrost is also very good because it can be ported to other applications, such as 3ds Max. It's not immediately obvious, but the Bifrost extension also includes another plugin, the Bifrost Procedural for Arnold. This bit of software allows Arnold to render Bifrost shape nodes directly without needing to be converted to traditional Maya shape nodes. Bifrost expands, amplifies, and accelerates the capabilities of the host application. Knowing that, we can better appreciate the significance of the name Bifrost. It's an English corruption of a proper noun Bifrost from Old Norse mythology. Bifrost is the rainbow bridge between earth and heaven. Maya is the illusion of the world, and Bifrost is the bridge to a brighter, better, more magical world of the gods. In order to use the Bifrost extension, we need to make sure that the appropriate plugins for Maya are all loaded. I've got a stripped down version of the Maya interface for teaching purposes in which I've hidden some of the panels such as the shelf. If we go into the Windows menu, we can see under UI elements I have several of these items hidden. And I've also hidden the panel toolbar here using the keyboard shortcut, which is Control-Shift-M. So let's make sure that the Bifrost plugins are enabled. You can always determine whether those plugins are enabled or not by going to the Create menu. And if you see Bifrost Graph listed there, then the plugins are loaded. Let's take a look at the plugin manager just to make sure that we know where those plugins are to be found in case Bifrost is not loaded. Go into Windows, Settings Preferences, Plugin Manager. And scroll down. There's an entire section for the Bifrost plugins. And we do want to make sure that they are all loaded and that they load automatically. So that is the case here. We see checkboxes next to all of those items. For Bifrost, there is one extra little wrinkle that we need to pay attention to, which is there is a separate plugin called the VNN plugin, which also needs to be enabled. And if we scroll down a little bit, we'll see that there is another section here for Bifrost. The Maya VNN plugin must also be enabled for Bifrost to work. All right, so I've got those plugins loaded up, and I can launch the Bifrost extension in numerous ways. I can go to the Create menu and choose Bifrost Graph, and that opens up the Bifrost Graph editor and creates the Bifrost Board node. We can see that in the outliner if we open that up. We can go to Windows, Outliner, and I've got it docked over here on the left. Now we've got a Bifrost Graph node listed here. And as I mentioned previously, it's actually a dependency graph node, not a DAG node. So it has no transforms. It doesn't exist in 3D, but it has inputs and outputs allowing us to connect it to the Maya scene. That's how to load the Bifrost extension plugins. The Bifrost extension ships with some example graphs and scenes to help you get started. And we can find those in the Windows menu. we'll see an item for Bifrost Browser. We can access the browser from that item, and we see we have some categories of different types of sample graphs. We can also get to this same Bifrost browser from within the Bifrost graph. So if I close this window, go back to the main menus to Windows, Bifrost Graph Editor. If there is no graph in the scene yet, then we get this window, and it allows us to create a new graph or to launch the browser. I can click on Bifrost Browser, and it takes me back to this same window again. Some of these items have scenes associated with them, like this flame torch one. When I select that, down at the bottom, I see a message reading, Open Selected in Example Scene. If I click that, it will open up a Maya scene which includes this Bifrost graph. If I click the Import button over here, then the graph will load, but the Maya scene will not. Let's just keep it simple. I'll go for this one, Standard Explosion, which does not have any scene file associated with it. And I'm doing that for a couple of reasons. One is the scene files may or may not actually be set up well in order for us to understand how that graph works. I have encountered some issues with the sample scenes, so just be aware that they're not intended for production use. They're there for you to analyze and take apart so that you can create your own effects. But the standard explosion doesn't have any scenes, so we won't have any issue with that. So with that selected, I'll click the Import button. And although at the bottom it'll say that the file was read in a very short period of time, it may take a moment for the graph to actually compile. So if you try to navigate in Maya, you may find that it hiccups for a couple of seconds. Don't be alarmed by that. It's just compiling this graph in the background. But after a couple of seconds, it will have compiled. And then you can navigate in the graph using the standard Maya keyboard shortcuts, middle mouse button, drag to pan around, Alt and right mouse button to zoom in and out. So we've got some nodes in here. These are all very high-level nodes that have many functions built into them. And it's really out of scope for us to analyze every one of these. But we can take a look at these in the following movie. I'll just mention that this particular graph does not have any input to Maya. It actually generates everything from within this graph, including an implicit geometric sphere. I'll also point out that some of the nodes have these backdrops around them, and this is a way of commenting in the graph to give information to anyone who opens that graph. And we can see here that this vary temperature compound has a note here saying, varying the temperature will produce a less uniform blast. We can find more information about the graph or any selected node by going over here to the right-hand panel. It's got two tabs, Parameters and Info. And if Parameters is active and we select a node or compound, we'll see the parameters or attributes for that compound or node. If we go to the Info panel, we'll see documentation on that node or compound. That's how to load an example graph from the Bifrost browser. In the previous movie, we loaded one of the sample graphs from the Bifrost browser. I've got that loaded in my Maya scene here now, and we can actually see the explosion if we play the timeline. I've got my time slider hidden, so I'll just unhide that. UI Elements time slider. And press the play button, and that will cause the simulation to start immediately on frame 1. And we can see in the active perspective view we're getting a fireball. To stop the simulation, you can hit the escape key. You can see that down here in the help line. Pressing the stop button may not actually stop the simulation. Additionally, you'll need to wait for Bifrost to finish working on the current frame. And if your simulation is taking a long time per frame, that means you may need to wait a long time for Maya to become responsive once again. And there's really nothing we can do about that currently. Bifrost is just built that way. So when you hit that escape key, you may need to wait for a while to get your Maya interactivity back once again. Let's analyze this graph and just see its major components. We can go back to the Bifrost graph from the Windows menu, Windows, Bifrost Graph Editor. But if we don't have any graph selected in the scene, then we strangely get this screen once again. So this is another bit of a bugaboo with the current version of Bifrost. If you press the plus sign over here, then it will show you a list of all of the graphs that are currently in the scene. And so I can choose the one that's in the scene now, which is Standard Explosion, and that loads up the graph. There is another way to do this. If we close the graph window again and open up the outliner, if we select the graph node in the outliner before launching the Bifrost graph window, then this graph will load automatically. So that's really the preferred workflow. Select your graph in the outliner, then go to the Windows menu and choose Bifrost Graph Editor, and it will load the graph automatically. So let's take a look at what we've got here. I'll maximize this window. We'll see that we've got a Create node here. Bifrost is creating a sphere, and that's actually a polygon object generated directly by Bifrost. And so there is no input node here. We're not grabbing any geometry in Maya. Then we see there's a vary temperature compound, and that is, as the name implies, varying the temperature, which is going to cause the explosion to have a varied look to it. It won't be perfectly uniform. Then that's being piped into a source air compound. And again, if we select one of these compounds over on the right side, we'll see in the info panel some helpful information that tells us what that node does. In this case, these are really the source parameters for the air or the atmosphere in which this combustion effect is taking place. And it has very important properties such as the voxel resolution or the size of individual elements in the simulation. Moving on, I can navigate with the middle mouse button. We'll see there's also a source fuel compound or node, and that is determining the properties for the combustion fuel. And that is feeding into the Simulate Aero node, and that is where the simulation actually takes place. And it's the most important node in here. It's taking inputs from the air and fuel into the sources section. It's also taking inputs from these solver settings, which determine the exact properties of the simulation, how it's going to behave. And the Simulate Aero node is also taking an input from this collider node. And currently there are no colliders in the scene, but when you create an Aero simulation, you get a collider node or compound just by default so that you can wire that up. The output of the simulation is going into an assign material compound, whose job is to, as the name implies, assign a material. And there's a material in the Maya hypershade, and this explosion material node is referencing the hypershade node. So this is actually an input from Maya, and it's being assigned with this assign material node. And then finally, the assign material node is going to the output, which results in the fireball we see in the viewports. That's a quick analysis of one of the example Bifrost Browser graphs showing the data flow for an Aero combustion effect, which is the standard explosion. Picking up from the previous movie, I've got the standard explosion graph open in the Bifrost graph editor. I'd like to talk about navigating inside of the components to see that the graph is hierarchical in structure. Some of the nodes in this graph have an icon indicating that they are a compound, which is a combination of nodes. And actually, some of the compounds have different icons. For example, this source air compound has got an arrow icon. But a generic compound icon looks like this. It looks like a bunch of nodes connected in a little mini graph. If I double-click on one of these compounds, I'll go inside that compound to see its structure. And we can navigate here in the usual way using the middle mouse button to track or pan and zoom in with Alt and right mouse button. And as we do, we see that this compound is kind of complex. Also notice that we see a message down here in this particular case. It says, not editable, referenced. And that means that the compound that we're inside currently is loaded from disk. and we're not actually able to make any changes to this graph. We'll talk more about that in a little while. Right now, I just wanted to show you how to navigate inside the hierarchy of a nested compound structure. Some of these other nodes in here are compounds themselves. For example, we got one here labeled Create Sphere Points, and it's got a compound icon. If we double click on that one, we'll go inside there and zoom in a bit, examine this, and we'll see that we've got more compounds inside of compounds. And as we go deeper into that hierarchy, we will see we've got a trail of breadcrumbs up here at the top, telling us exactly where we are inside that graph node structure. And again, I can double click on a compound and go inside that one. The hierarchy can be arbitrarily deep, and it will not be unusual at all to see compounds that have structures that are nested up to 10 levels deep or more. So don't let your head explode when you contemplate the complexity of this. The compound structure hierarchy exists in order to help us manage that complexity. Imagine if all of this was at the root level of the graph. There's just no way we'd be able to work with hundreds or thousands of nodes on the screen at once. To navigate, all we need to do is click on these breadcrumbs up here, and we can go back up even to the top level of the graph. That's how to navigate nested compounds in a hierarchical graph structure. Now we know enough about the Bifrost graph in order to make our first attempt at building a graph using the stock compound, which is the basic Aero graph. We'll want to have some sort of object to generate the Aero simulation, and we can use any Maya mesh object to do that. So let's keep it simple. We'll just create a sphere. Go to the Create menu and choose Polygon Primitive Sphere. With that object still selected, we can make it an input to the graph automatically. So P-Sphere 1 is currently selected. We can go back into the menus to create Bifrost graph. And when that graph loads, we see there's an input node in it. And if we select the input node in the parameters, we see the path to the object that was selected when we created that graph. And we could actually just type this path in directly to any input node to grab the shape node for any object in the Maya scene. It just has to have this syntax. It has to start with a slash, then the transform node name, another slash, and then the shape node name. We can also just simply middle mouse drag nodes from the outliner, and that has the convenience of changing the name of the input node for us. So let's delete this input node. I'll select it and press the delete key. Go to the Maya outliner and middle mouse drag the sphere into the Bifrost graph. And it's labeled P-Sphere Shape 1. We've got an output node automatically. And if we click on the mesh port of that input node labeled P-Sphere Shape 1, we can drag over to the plus sign on the output node, release the mouse, and a connection is made. And in the process, a new port was created on that output node, and it's labeled Mesh 1. Once we've connected something to the output node, now we actually have an output here in the outliner. It's the Bifrost shape node, Bif1. Just for a moment, I'm going to investigate that by minimizing the Bifrost graph editor. I'll select that Bif1 node, which is actually the transform of that Bif shape node. Grab the Move tool and just move it over to the side just to show that we now have an input object, which is the original P-Sphere 1, and an output object, which is the Bifrost shape. Okay, I'm just going to send that back to its original position. Set its translate X value to 0. And go back to the Bifrost graph editor once again. Now that we've got inputs and outputs working, let's actually create a simple basic Aero graph. And we can break the connection that we have here. There's a keyboard shortcut for that, which is to hold down Shift and Alt and click and drag across that connection, and that'll break the connection. Now we're ready to create a new basic Aero graph. And the way to do that is to press the Tab key in the graph. And you'll get a pop-up menu with a list of categories of all of the installed nodes and compounds, and also a search field. And if you know the name of what you're trying to create, then you can just type it in here. And in this case, I know that I'm looking for a basic Aero graph. So I can just start typing that in, BAS, and it actually is the first one in the list, basic Aero graph. Click on that, and we get a new compound here, basic Aero graph. And I know that this is a referenced compound because it's got a little blue diamond next to it. And that's Maya iconography to indicate that this is a reference. It's a link to a file on disk. And if I double click on that node, we'll go inside it. Let's maximize the graph editor so we can see better. And inside that referenced basic Aero graph, we see a bunch of other compounds. Let's just automatically organize the graph here with the keyboard shortcut, which is L. As we saw earlier, we've got some high-level compounds, including the simulation node, source air, collider, and Aero solver settings. And we've also got an input and output node. And those exist in order to make connections outside of this nested compound. In other words, we need to connect to what's happening here at the top level of the graph. So if we go back into that basic Aero graph, we'll see that we've got an input and output, but they're not connected to anything. And we also see down here at the bottom, because we went inside a referenced compound, we're not able to edit the structure that we see in the graph here. In the current condition, we actually cannot use this graph. We can't connect these inputs and outputs to anything here because this compound is not editable. Well, that's kind of strange. We could make this editable. There is a way to do that. We can go back up to the top level here and right-click on that compound and choose Make Editable. Once we do that, the little blue diamond disappears, and now this compound has been imported into the current graph in the current Maya scene. But the compounds inside this compound have not been imported. So if we double-click and go inside there, we'll see that although we're able to make and break connections, the compounds internal to this compound are still referenced. And that tells me that the Make Editable compound command is not recursive. And that really is the case across Bifrost. The commands are not recursive in general. Okay, we could connect a whole bunch of stuff up to these input and output nodes to expose them at the higher level of the graph, but that's way more work than we really need to do. There's an easier way to do this. So I'll go back up to the top level of the graph and use the undo command to go back a few steps. I'll just press the Z key once and press the Z key again. And now we're back where we were with a referenced compound. Instead of making that compound editable, we can explode the compound. And that's going to actually make things a lot easier in this case, and that is the preferred workflow with one of these basic graphs. So you bring that graph in with the Tab key, and then immediately right-click on it and choose Explode. And we can reorganize the graph once again. Click in the graph and press the L key. When we explode a compound, that compound gets deleted and its contents are promoted to the current level of the graph, in this case the root level. The internal input and output nodes inside that compound are deleted as well. And again, these nested compounds are not exploded, nor are they made editable, because that explode command is not recursive. But now we're in a good position to actually make the connections we need to make. So we can just bring our input node over here and connect its mesh output to the geometry input of the source air compound. Then over here we have the simulate compound, which is the engine that runs the simulation. We want to connect its Aero volume port and create a new port. So drag over to the plus sign and release the mouse, and we get a new port labeled Aero volume. And we don't need this mesh port anymore. It's not connected to anything, so it's not a problem. But if we want, we can just right-click on the port, and from the pop-up menu, choose Delete Port. And we just clean that up. So now we've got a basic Aero simulation, and we can minimize the Bifrost graph editor. Maybe get a little bit closer in the viewport here, and press play. And that will make the simulation run. It'll take a moment, but we'll start to see some Aero volume effect appearing, and it's being emitted from the sphere that we created in Maya. And that's how to create a new graph using the stock basic Aero graph compound. Because Bifrost is separate from Maya, we can treat Bifrost compounds as assets within Maya. And we can install those compounds to a special directory to make them show up within the Bifrost graph, allowing us to easily share compounds that were created by other users or even downloaded from the internet. So let's talk about where to install these compounds. I've created a compound for this course, which is a simplex noise deformer. And to use it in the Bifrost graph, we'll need to install it to the appropriate directory. Let's investigate where that is. We can find that information in the help documentation. Within the Bifrost graph editor, we can go to Help, Bifrost Help, and it launches the web browser, takes us to help.autodesk.com. Over on the left is the navigation pane. Open up Working in Bifrost Extension and click on Install Compounds and Graphs. And this tells us where we need to install our compounds or graphs for the various operating systems, Windows, Mac, and Linux. And basically, they just need to go inside the current user's home directory in a folder created during the Bifrost installation called Autodesk Bifrost Compounds. And I've got that prepared already. Here's my home directory, and there's a folder in there called Autodesk. Inside there, Bifrost and Compounds. Currently, that folder is empty. I could drop my compound file directly into this folder, but it's a better idea to keep things organized with subfolders. So I've done that. I've got in the exercise files a JSON file, which is the compound, and it's already inside a special folder just to make sure that we don't get it mixed up with any other compounds we might install later. So I'll open that window as well. Here's the exercise files. It's a Maya project, and I've created a custom folder in that Maya project called Bifrost. Inside there is a folder called Compounds. Inside there is a folder called LinkedIn, and that's going to be our folder in the Bifrost Compounds folder over here. Inside that LinkedIn folder is the actual deformer file, which is in the format JSON. I'm going to select this LinkedIn folder, right-click and copy it, and go over to the Bifrost Compounds folder, right-click and paste. And once again, I've created that subfolder LinkedIn just to make sure that I don't get my deformers mixed up with anything else that I might install later. Okay, to make that show up in the Bifrost graph editor, I'll need to restart Maya. So I'll exit and restart. Back in Maya, I've got my very simple Bifrost graph with no geometry in the scene yet and no connections to anything in the scene. But I have installed that JSON file, and I can load that custom deformer by pressing the Tab key. And now I've got a new category here, User, Deformers, and I can click Simplex Noise Deformer to create that compound. As expected, this is a referenced compound as indicated by the blue diamond up here. That means that this is loaded from disk and not editable, but of course I could always edit it if I needed to by right-clicking and choosing Make Editable, but we won't need to do that in this case. That's how to install a custom compound to the user's home directory to make it available within the Bifrost graph. Later in the course, we'll look at how to create compounds and publish them ourselves. Now we're ready to construct a graph to perform some work, in this case to displace a polygon mesh surface. I've provided a deformer, but we need to construct the part of the graph that actually moves the points or displaces them away from the surface. I'll minimize the graph editor, and let's create a test object. It'll just be a polygon torus. Create polygon primitives torus, and with it selected, go to the channel box to its input node to polytorus1. Just increase the radius to a value of 10. Press Tab and set the section radius to a value of 3. Now let's bring that into the Bifrost graph. I'll bring that back up again. From the outliner, middle mouse click and drag ptorus1 into the Bifrost graph. And now we've got another input node. I'm going to keep this input node in here because we'll need that later. I want to connect up these various parameters or attributes so they can be exposed in the Maya interface. And I could connect them to this input node, but I actually want to keep them separate so that if I want to, I can easily swap out this object for another object without having to deal with changing paths or anything. And I won't mess up the work that I've done on this other input node. So that's my general process here. I'm going to keep this input node for all these parameter inputs and this other input node for the actual geometry. Let's connect it to the deformer. Click and drag from its mesh output to the mesh input on the deformer compound. Now we'll start to work on creating the displacement part of the graph. The general process for moving points on a mesh is to get the positions of those points and then add something to those positions and then reset the positions to their new locations. So we're going to get the point positions first, and there's a node for that. Press the Tab key and type in GET_P, and we get point position. So create that node and connect it up to our mesh shape. We also need an add node to add something to the positions. Press the Tab key again and type in ADD. Create an add node. And we get a warning message down here, but that's just because the add node is not connected to anything yet. Connect it to the point position. And then we want to take the result of that add node and set the point positions on the mesh. So once again, press Tab, and this time type in SET_P, set point position. Connect the output of the add node to the positions input on the set point position node. And we also need to supply the original geometry. So we'll connect the p-torus shape mesh output to the geometry input on that set point position node. And now we've basically got the skeleton of changing the positions of points. We just haven't actually changed the positions. Let's now connect that set point position out geometry port to the final output of the graph. As soon as we do that, now we have a BIF shape in our scene. And we can just actually select that, BIF1, select this transform node, and just move it over. And we can now see that we've got two separate toruses or tori. Here's the original Maya shape, and here is the Bifrost shape. All right, so we'll go back to our graph, and just as a proof of concept, we want to add something to those positions. We're not quite ready to add the deformer position because we have to wire up a bunch of other stuff first. So just as a proof of concept, we'll add just a value to the point positions. So we'll need a value node. In the graph, press the Tab key and type in value. Create a value node and connect its output to a new port on the add node. And with that value node selected, we'll see that it has a value field, and we could enter some value in there like 2 or 5. And what that's doing is it's adding this value to the positions of all the points in scene units or grid units. And it's doing that in world space. And additionally, it's moving the points in all three axes, X, Y, and Z. If I go back to the Move tool, we'll see that we've got an offset between the actual point positions and the original pivot point on that BIF shape. It's a little bit more dramatic if I set that value to 10. So we're moving it in positive X, positive Y, and positive Z. If we want the ability to move in all three dimensions separately, then we can change the type of data coming out of this value node. We can see that the current type is float, which is a single number with a decimal point. We can easily change that by clicking on this button here. Little ellipses button launches up the Set Value Type window. We can choose the Vector tab and set it to 3 components. And down at the bottom it says Type, Math, Float 3. This is what we need for an X, Y, and Z position. Click OK. Now we've got 3 values, and we have independent control of the 3 X, Y, and Z axes. So for example, I can move it down in the y-axis by giving it a negative value. So we've got a proof of concept on moving positions of points on an object. In the next movie, we'll look at changing those point positions in the space of the object's surface, or its normals, instead of in world space. In the last movie, we set up a very basic graph to change the positions of points on an object, and we're moving those positions in world space currently, but we want a displacement effect, and of course that's going to operate in the space of the surface of the object, or in its normal space. So we need to integrate the information about the object normals into our graph, and that will be done with another node called getPointNormal. So press the Tab key, type in get_p, and we've got getPointNormal. And that needs to be connected to our mesh output. So here's our p-torus shape. We'll want to connect that mesh output to the getPointNormal geometry input. Once that connection's been made, we can use that to modify the position values that we're adding. And we want to multiply these point normals with whatever value we're adding. So we'll need a multiply node. Once again, press Tab, start typing in MULT. There it is, multiply. So we'll take the output of the normals and connect it to a port on the multiply node. And we've also got this value node down here. And that is what we're currently adding to the point positions. We want to multiply our normals with the value. So we'll take the output of the value node, plug it into a new port on the multiply node, then take the output of that multiply node, connect it to the add node. So we're taking the point normals, we're multiplying it by some value, and then we're adding that to the point position. So if we look at our scene here, we've got some strange results, but that's because we've got some strange values over here. So we'll go back to our value node, and let's just give everything a value of 1 in all dimensions. And what we're effectively doing here is we're increasing the volume by moving each point along its own normal by the same amount. And if we gave these all values of 5, for example, we will have moved each one of those points along its own normal by 5 units. Okay, so for a height displacement effect, we actually don't need this vector. We could do a vector displacement, but actually the output of my deformer here is a float, and it's not a vector. And so we really should just use a single floating point value. So we can go back to our value node and switch its type back. And go back and browse and change it back to a simple floating point. And now we've only got one value again. And so with this setup, we're only going to be deforming the object along its own normals using a standard height displacement effect. And we won't have to worry about the complexities of a vector displacement effect. And we won't need to worry about the fact that our deformer is only outputting a float. That's how to manipulate vertices along their own normals using getPointNormal. As we've seen, we can control the Bifrost graph parameters by selecting nodes and changing their values in the parameters pane over here. But for various reasons, we will need to expose certain parameters to Maya. And we do that through the input nodes. We've currently got 2 input nodes. We've got one for the mesh object and another empty input node that just came along when we created the graph in the first place. What I want to do is expose the displacement amount to Maya. So I'll be able to change the displacement amount from the channel box or the attribute editor. Currently, I've got a value node that's driving the amount of displacement. So I can change that value to 4 or whatever, and we can see how that's affecting the displacement amount. Let's expose that to Maya. And it's as simple as dragging from a port to the input node and creating a new port there. So now, instead of this value node driving the displacement amount, I've exposed that parameter to Maya. And before we do anything else, I do want to rename these so that we'll know what we're dealing with. Get in a little bit closer here. right-click on that new input port and rename it. Let's call it displacement underscore amount. Click OK, and that renames this port. It did not rename the port on the multiply node, and in fact, there's no way for us to do that manually. We can't just right-click and rename that port like we can on the input node, but we can inherit this name by making this connection again. So let's disconnect this, hold down Shift and Alt, and drag across that connection to break the connection, and just recreate the connection, and now we've got the name inherited. Okay, so let's now investigate changing that displacement amount from Maya. If we select the Bifrost graph node in the outliner, we'll see that we've got displacement amount X, Y, and Z. Well, we're back to a vector. And the reason that has happened is because the ports are automatically inheriting data types. We connected a normal here, which is a float3 or XYZ data type. And so Bifrost just assumed that we wanted a vector data type for this other multiply port. But we can change that pretty easily. We just need to change the type of the port on the input node. Right-click on that displacement amount port, and from the pop-up menu, we could set a value type, or we could choose from the history of recent value types. Let's choose float. And as soon as we've done that, it changes to a different color. That light green color indicates a float, whereas this sort of chartreuse color indicates a float3 or a vector3. And over here in our channel box, we see we've got a single value now. Again, we're only displacing in the height along the normals. We're not doing vector displacement. So I can change this value, change it to a value of 5 or whatever. We've just exposed that displacement amount parameter to the Maya scene graph. I also want to connect the rest of these ports here on the deformer. So let's maximize the Bifrost graph, make it a little bit easier on ourselves, and just wire up the rest of these. We can see that they are of different data types. Some of them are floats, some of them are vectors, and there's different types of vectors as well. This first one here, deformer frequency, is a float. And we've got deformer seed, and that's a different color. That's actually an integer, doesn't have a decimal point. Then we have deformer position, and that is a float3 with this chartreuse color. And finally, we have the object transform matrix, or XForm matrix. And that port and its connection wire are red, indicating a data type of vector4 or float4, because the matrix has 4 values instead of 3. So we made all those connections, and if we minimize the graph, back in our channel box, we can see that we've got a bunch of new attributes there that we can change. Currently, changing these will not perform anything because we've not wired up our deformer yet. Notice that the transform matrix, or position rotation scale that we wired up, is not showing up here. And we need to make that connection in the Maya node editor. We'll see that in the following movie. That's how to expose parameters to Maya as attributes of the Bifrost graph node. In the previous movie, we saw how to expose various Bifrost graph parameters to the Maya scene graph. For example, to allow us to control things like the deformer frequency from the Maya attribute editor or channel box. Now we need to look into connecting up the transforms of objects so that the position, rotation, and scale of objects in the scene will affect our Bifrost graph. And we need to do that in this case so that the simplex noise deformer compound will operate in the local space of the deformed object, and additionally so that the deformation or displacement will be proportional to the object scale. So you see that we got several connections here, including one called Object XForm Matrix. And XForm is short for transform, and the transform matrix is the combined position, rotation, and scale of an object. Remember that in Maya, transforms and shapes are dealt with separately. We brought the shape in as a mesh input, and now if we want our deformation to operate in local space, then the graph needs to know the position, rotation, and scale of the object, so we'll need to bring the matrix in as well. That will be done through the Maya node editor. So I'll minimize the graph editor, and select the two things that we want to connect. pTorus1's transform node and also the Bifrost graph. So hold down Control and select both of those. Go to the menus and choose Windows, Node Editor. And we don't see all the connections that we need, so click to select nothing, and then press the 4 key on your keyboard, and that's the same as clicking the icon here to show the custom attributes. So here's the torus shape node. We don't need that. We need pTorus1, which is the actual transform node. And we want to connect its matrix output to the matrix input on our Bifrost graph node. And again, we need to do that so that the deformations will operate in local space, and it won't matter how we've positioned, rotated, or scaled the original source geometry. Having made that connection, we can close the node editor and go back to our Bifrost graph. We've got almost all the connections in place here, and we're ready to wire up this deformer to actually change the displacement. And that can be done by simply taking the noise output here and connecting it to the existing multiply node to make a new port. So now we're multiplying the normals with the displacement amount with the deformer. So we can now test this. We can go back to the scene graph, and with the pTorus1 object selected, we can go down into its shape nodes. So we've got the inputs and outputs here. First, let's play around with the outputs. We'll go into Bifrost Graph 1, and we've got the deformer frequency. Well, with a 0 frequency, we won't see any deformation. So let's increase that deformer frequency to, let's say, 0.5. And now we've got some deformation there. Okay, so we don't have very much detail on our source object. So we can go into the input nodes to polytorus1, increase the subdivision's axis to 100, press tab and set the subdivision's height to 50. And now we're getting a very strong displacement effect. Back in the output nodes, we've got more toys to play with. I'll just minimize the Bifrost graph for a moment. We've got deformer position X. That changes the position of the deformation effect relative to the object. So I can select that name and middle mouse drag from left to right in the viewport, and we can see how that's shifting the effect. And of course, we can reduce the displacement amount too. We can bring that down to, let's say, 0.5 or maybe 2, and maybe reduce the deformer frequency to 0.2. And now we've got a pretty classic deformation here with a simplex noise. And this is all happening in local space because we connected up the matrix. And we can see that if we grab the Move tool and position the original object or rotate the original object, and our Bifrost shape is staying constant. I'll undo that. However, if we transform with the Scale tool, what we'll see is a little bit different. The deformation is not changing according to the scale. So as we have a small object, we're seeing a lot of deviation relative to that small object. And with a large object, we're not seeing quite so much displacement. We want the displacement to be proportional to the scale. So let's restore all those scale values to 1 and go back to our graph. And we want to multiply the scale by the displacement amount. So we've got our transform matrix here, but it's in a format that we can't really use in this case. We just want to extract the scale, and that's done with a node called matrix to SRT, or scale, rotate, translate. So press the tab key, start typing in matrix. There it is, matrix to SRT. And we want to connect that up. Take the output of the object XForm matrix port, plug it into matrix to SRT. Then take the scale output and connect it to our existing multiply node and create a new port. And once that's been done, we should see the result that we want. As we scale the original object up or down, the displacement on the Bifrost shape is proportional, and it doesn't change shape as we scale the original object. All right, I'll undo that and set it back to a value of 1. That's how to work with transforms in the Bifrost graph. We've got our simplex noise effect working, and we can demonstrate that if we select our torus object and go into its output nodes to Bifrost Graph 1 and make adjustments to these various attributes, such as the displacement amount. You can select that name and middle mouse drag to access the virtual sliders and set that displacement amount, or the frequency. We can set that to a higher value, maybe 0.3. And the seed, which is the randomness, we can set that to some other integer value like 4 and get a different pseudo-random result. Or again, we could change the position of the deformer relative to the object using the middle mouse button to position that deformer. So it's basically working exactly the way we want it to, and it's preserving the position, rotation, and scale coming from the original object so that all the deformations happen in local space. At this point, we can save out our height displacement as its own compound. So I've got the Bifrost graph open already. I'll bring that up. And basically, I want to select everything here that's not an input or an output or this existing simplex noise deformer compound. All right, so everything that's not an input or an output or the simplex noise deformer. So that includes the get point normal, get point position, matrix to SRT, multiply, add, and set point position. Drag a rectangle to select all those, or maybe use the control key if you want. But select all those and create a compound. We can do that by going to the Create menu, Compound, or we can use the keyboard shortcut, which is Control G. So let's try that. Control G. Now we get a new compound. And it's like magic. It creates all the necessary input and output nodes and names them appropriately. So if we double click on this new compound, we can go in there and investigate. Let's press the L key to auto layout. So here are all the nodes that we selected, and those all got placed into this compound, and we get an input and an output automatically. Let's go back up to the top level, and we can rename some things. Let's rename the compound itself. We'll call it height displacement. We can also rename this port down here. It just inherited the name of the incoming connection, which is noise. Right-click on the port itself and choose Rename, and we'll call it Deformer. So now we've got a nice compound that we can use in other graphs if we want. And to make that easy, we can just publish it to its own file. So with that compound still selected, we can go back into the Create menu to Publish. Or we can use the keyboard shortcut Control P, or we can right-click on the compound and choose Publish. The Publish Compound window pops up, and we need to supply some information here. We need to tell Bifrost where to save the file, what file name to use, what category for it to go into, and what the compound name will be in the graph. Well, we have the compound name filled in automatically here, just inherited that from the actual compound name here. So let's copy this because we'll need to plug that into the file browser. So select the compound name, height displacement, and copy it with Control C. Then we want to choose the file location to save this new document. And by default, it's going to save into the current user's home directory, Autodesk Bifrost Compounds. But previously in the course, we created a subfolder in there called LinkedIn in order to keep our various compounds organized. So let's continue on with that practice. Click the Browse button. And in our current user's home directory, Autodesk Bifrost Compounds, we previously created a subfolder called LinkedIn. And if you didn't do that exercise, then you won't see that here, but you can create it now. Then let's go inside that subfolder and paste in our file name here, Control V. Click Save, and that doesn't actually save the file. It just saved the path to which we're going to save that file. The compound name is already in here. The compound namespace is the default, which is user::compounds. And that's a little bit too generic. I would like to keep my compounds organized by categories that make sense. And so we can save our height displacement into a category called Deformers. And if you did do that exercise in which we installed a new compound, then that namespace will exist here. If you click on the pull-down list, scroll down to the bottom, you should see User Deformers. You can select that. Now, if you didn't do that exercise, then you won't see that listed there, but you can just type it in, user : deformers. And just click Publish. Now that file's been saved out. And we can test it immediately. Just press the Tab key and then go to the categories User, Deformers, Height Displacement. Click on that to create another node which is identical to this one, but this one is a referenced compound, as we can see by the little blue diamond there. So that is how we can publish a new compound and use it in a graph. If I wanted to, I could delete this one and wire up the new one that we just created, but there's no compelling reason to do that in this case. So I'll just select that and delete it. All right, so we can press the L key in the graph and admire our work. So we've got our input nodes here on the left. We've got two compounds, one that I supplied and one that we built from scratch, and our final output node here. That's the basics of how to construct a graph in Bifrost, and also how to encapsulate nodes into a compound and publish them to a file for use in other graphs. We've created a displacement effect on this Bifrost shape here. And if we try to render this, we might encounter some issues requiring us to convert it to a Maya shape. First of all, if we look closely, we'll notice that the shading looks kind of strange on the surface here. And that has to do with the surface normals. We didn't actually reset the surface normals in our graph. If we try to render this, it won't really look right. So we can address that by going back to our graph. Go to the Bifrost graph in the outliner, and then go to Windows, Bifrost Graph Editor. We just need to insert a node here to reset the normals. So press the Tab key and type in the word normal, and you'll see Update Mesh Normals in the list. So click on that and simply connect that in between the set point position and the output. And then we can minimize the graph and go back. And we can see now that our mesh looks much better. Those normals have now been reset. So that's half of the battle here. The other half has to do with support for the Bifrost shape itself in various rendering engines. And that actually includes Viewport 2.0. The viewport itself does not have full support for the Bifrost shape yet. We can see that if we turn on lighting. We can press the 7 key to enable lighting in the viewport, and also turn on shadows. Go to the menus and choose lighting and enable shadows. And we see that we have a shadow from our original Maya shape and no shadow cast by the Bifrost shape. I've got a point light here. We can select that and move it around just to verify that the shading on the Bifrost shape is correct, but we're not getting any shadows. If we render this in Arnold, we will get the shadows. And we can see that if we go up into the viewport menus and in the renderer menu choose Arnold and start the interactive production rendering. That'll take a moment to start up, but once it does, we'll see that in fact we are getting shadows in Arnold. And we can select that light in the outliner and move it around and see how that updates interactively. Arnold has full support for the Bifrost shape. But if we try to render the Bifrost shape in any other renderer, including Viewport 2.0, there will be some issues and some unsupported features. Let's go back to Viewport 2.0 as our renderer. The workaround for this is to convert the Bifrost shape into a Maya mesh. And once that's done, any renderer that supports Maya will render the Bifrost shape correctly. To do this, we'll want to go into the Maya node editor. Select the Bifrost graph in the outliner and go to Windows, Node Editor, and click to graph the input and output connections on the selected node. And click to deselect everything and press the 4 key to display custom attributes. So we have the Bifrost graph here, and it's got an out geometry port. We want to connect that to a node to convert the Bifrost geometry. So click in the graph and once again press the Tab key and type in the word Bifrost, and we'll see Bifrost Geo to Maya. So click on that to create that node and click off of it, and once again press the 4 key. Connect the out geometry of the Bifrost graph to the Bifrost Geo input on that conversion node. And then we need to send this to a Maya mesh shape. So once again, press Tab, type in the word mesh this time, and click mesh to create that Maya mesh shape. And once again, press the 4 key to show custom attributes. We want to connect the Maya mesh output to the input mesh on this polysurface shape node. So open up the Maya mesh on that Bifrost Geo to Maya node and connect Maya mesh 0 to the in mesh port on this shape node. And that should do it. If we minimize the node editor, we now have polysurface 1 in our outliner, and we can just move that over, deselect it, and it renders in green in the viewport, which indicates that there is no shading group attached to it. So select it, right-click in the viewport to get the marking menu, and near the bottom choose Assign Existing Material, and we can choose Lambert 1, or we can use the new Autodesk Standard Surface. Let's choose that, Standard Surface 1. And once we do that, now we have proper shading and shadows as well. You'll need to do that process for any renderer that does not support the Bifrost shape directly. Arnold, of course, does. So if you're just rendering in Arnold, you actually don't need to do much. You might need to reset the normals as we did here, but you don't need to convert to the Maya mesh shape. That's how to use a Bifrost Geo to Maya node to convert a Bifrost shape to a Maya mesh. Assigning materials in Bifrost can be done in numerous ways. In the previous movie, we saw how to assign a material to a Bifrost shape that has been converted to a Maya shape. And that's just done in the usual way that you would assign a material to any object in Maya. If you plan to render the Bifrost shape directly, however, you'll need to make the material assignment within the Bifrost graph. In this movie, we'll see how to assign a material that already exists in the hypershade. So let's open up that hypershade. And I've got a Blin 1 material available in here. And we want to drag that into the Bifrost graph. So select the Bifrost graph in the outliner and open up that graph from the Windows menu. All we need to do is just middle mouse drag the material into the graph. And this creates a material reference node. So if we select that node, we can see that it's pointing at a material name called Blin 1. To assign that to our output, we need a material assign node. So click in the graph, press the Tab key, and type in material, and we'll see assign material. And we need to wire this up. Connect the final output of our height displacement node to the geometry input of the assigned material node. Connect the output of the material reference to the surface material input on that assigned material node. With that node selected, we can see that we have the ability to set a surface, displacement, or volume material, just like we would in a Maya shading group. Take the output of that assigned material node and connect it to the Bifrost graph output. And that's all there is to that. We can minimize these windows. And now we've got that Blin material assigned to the Bifrost shape. And that will render just perfectly in Arnold. But again, as we saw in the previous movie, if we try to render the Bifrost shape in another renderer, we may run into some limitations. That's how to reference a hypershade material into the Bifrost graph. As we saw in the last movie, we can make a reference to a hypershade material within the Bifrost graph and assign a material to the Bifrost shape that way. We can also define materials directly within the graph, and those materials exist only within the graph and not in the hypershade. There are really only two material types supported currently, the Autodesk Standard Surface and a constant or flat color. So we're going to assign an Autodesk standard surface within the Bifrost graph. Let's select the Bifrost graph and go to the Windows menu and choose Bifrost Graph Editor. And as we did before, we'll need an Assign Material node. So click in the graph and press the Tab key and start typing in MAT, and we'll see Assign Material. And wire that up just as before. Connect the output of our displacement node to the geometry input of the Assign Material node. Connect the output of that Assign Material node to the final output of the Bifrost graph. And we also need a material node. So once again, press the Tab key and you can start typing in MAT, but don't go any further than that because the name of the material is actually Standard Surface Mat. And so if you type in material, it won't show up. You can also type in standard or surface, of course. So this is the one we want, Standard Surface Mat. Click on that and connect it to the surface material input on the Assign Material node. Select that Standard Surface Material node, and we'll see its parameters listed over here. In the current version of Bifrost, we don't have any color swatches or any kind of sliders or other widgets, so it makes it a little bit hard to work with, but we can change the colors and so on by changing numerical values. So here we've got the base color. We can reduce the red component to, let's say, 0.2, and we can see that color change. Or we can increase the specular roughness to, let's say, 0.8, and we'll see we get a rougher surface. That's how to define an Autodesk standard surface directly within the Bifrost graph and assign it to geometry. Dynamic simulations are typically history dependent, meaning whatever happens on a particular frame depends upon what happened on the frame before it. And for that reason, we can play a simulation linearly, but we can't jump around in the timeline, because if we jump to a particular frame, Bifrost won't have the information to calculate the data on that frame. We can see that if we press play in our timeline. We just want to make sure that we're not playing in real time, but rather playing every frame. So right-click on the timeline, and you want the playback speed set to play every frame free, or maybe play every frame max real time. We just don't want to be in real-time mode because then it'll skip frames and the simulation will break. So I'll set mine to play every frame max real time, and then press play. And we'll see a little bit of turbulence if we give focus to that camera view. This is a Bifrost Aero simulation in which a cloud is generated by a type mesh object, which is currently hidden. And I've applied influences here to move the cloud around with turbulence and wind. So again, we can play linearly, but we can't jump around in the timeline. If I press stop here and then wait a moment for it to finish working on the frames it's currently working on, then we'll get our Maya interactivity back in a second. And again, if I jump to a different frame, it will not actually work. Nothing updates up here because we would need to calculate all of the intervening frames. If you need random access in the timeline, for example, to integrate your simulation with some other animation, or if you simply need to render to disk, you'll need to create a file disk cache. And that's done in the graph. So I'll rewind. Select the Bifrost graph in the outliner and open up the Bifrost graph editor. And what I've done here is once again apply some turbulence and wind. And I've exposed those parameters in the Maya attribute editor and channel box so that I could animate those particular parameters. Basically the intensity of the turbulence and wind. I've set it so they will only start on frame 2 of the simulation. Okay, let's create our file cache. That can be done with some dedicated nodes, read cache and write cache, or it can be done with a sort of Uber node which incorporates the functionality of both. That's called a file cache node. So let's create that. Click in the graph, press the Tab key and start typing in FILE and choose File Cache. If you notice that you get a little bit of a hiccup there, it's because the Bifrost graph is actually recompiling when we change the graph. So if we want, we can pause the graph and that'll give us a little bit better performance. That's done from the Edit menu. We can choose Pause Graph Execution. Getting closer with Alt and right mouse button, we want to connect this file cache node directly before the output. So connect Simulate Aero to the Objects port on the file cache node. Connect the first object port to the out geometry of the graph output. With the file cache node selected, we can see in its parameters we have several modes. Read mode will read whatever's on disk, and if there's nothing on disk, then you won't get any output at all. From the pull-down list, we can choose write mode. That's what we want in this case. It's going to store files on disk. If we chose pass-through mode, then the file cache node wouldn't do anything. It wouldn't read or write, and it would just pass the simulation through as if the file cache node didn't exist. And the lazy mode is a read-write mode. We want the write mode this time. And we also need to supply a file path and a file name. I'll make this window a little bit larger here. Currently, in Bifrost, we don't have the ability to easily plug in our project folder, and we don't have any relative paths available here. All we can really do is paste in an absolute path to where we want these files to go. Now, by default, it's going to actually drop all your cache files into your current home directory. Not even in a subfolder, but directly in the current user's home directory. And that's seen here with this Windows environment variable $home. I need to replace that with an absolute path to my current project. And I've got that ready in the Windows Explorer window. Here's my current project, the exercise files. Within a Maya default project folder structure, there is a cache folder. So go in there, but there's no subfolder for Bifrost. We need to create that. Right-click and choose New Folder and call it Bifrost. Then go inside there, and we need to create a folder for the specific cache sequence we're going to create. Once again, right-click and make a new folder, and we'll call this one Cloud. Now we want to copy the path to that folder into the operating system clipboard. If you're on the Mac, the process for that is to right-click on the folder, then hold down the Option key and choose Copy as Path Name. On Windows, you want to go inside that folder, and you've got the path up here at the top of the Windows Explorer window. Right-click on the name of the folder there in that path, and then choose Copy Address as Text. Back in Maya, back in the file cache parameters, I'm going to paste that over this environment variable that says $home. So select that and paste with Control V. And we can make the window a little bit larger if we want. And we can go back to the beginning here and see that we've got a path to my current C drive, users, Aaron F. Ross. And notice that white spaces are allowed. And also notice near the end here that there's no problem with either forward or back slashes. So this file name field is pretty forgiving. We also want a name for the sequence. We just got the generic name here, file cache. Let's call it Cloud. So we're going to create a sequence of .bob files, and those are Bifrost objects. We're going to store all of the properties of the current simulation, because in the properties field we've got a star or an asterisk. So we've set this all up, and in the following movie we'll actually write out our cache. We've prepared to save out our simulation disk cache. We created the file cache node, and in its parameters we've set it to write mode, and we've plugged in the file path and file name for our cache sequence. And now we're ready to actually create the cache. I've paused the graph, so I'll need to unpause that. We could do that from the menus or with a keyboard shortcut, which is Control Period. I do recommend you memorize that keyboard shortcut Control Period to pause and unpause the Bifrost graph. You'll need to do that to prevent performance hiccups when you make and break connections or simply change parameter values in a heavy graph. All right, we're ready to create our cache. I'll minimize the Bifrost graph editor. Give focus to the camera viewport so we can see the cache being created as we go. Down in the range slider, we've got a button to control the playback mode. And by default, it's set to loop, but we don't want it to loop. We want to play once. So click on that button until you see a little number 1 there. It's very important that we don't set it to loop, because if it does, it will continue to write files over one another infinitely. We want it to play once and then stop. So we've set up all of the conditions, and all we need to do is press the play button. And as it plays, it's storing files to disk. And we can investigate that. We can see we've got some movement here. Let's go into our project folder. I've got that ready. And inside the folder that we created in the previous movie, we're starting to see some Bifrost object files. And notice the files are getting larger, and that's because the effect is taking up more volume in 3D space with each successive frame. And that also means that each frame will take longer to calculate. So as it plays through, it's going to get slower and slower. We'll let that finish. It'll take a few moments. When the simulation plays out and the timeline reaches the last frame, then you need to immediately go back to the Bifrost graph and switch it back to read mode. If you rewind or jump around in the timeline, you may invalidate some frames. So immediately go back into the Bifrost graph. I've got that minimized here. In the file cache node, change the mode over to read mode. We can go back to Maya, rewind, and play that back. We can see that playback much faster in this camera view. But each frame is taking longer than the one before it because it's loading a larger file for each frame. Here's a play blast of that cached Aero simulation. That's the process of writing and reading a Bifrost disk cache to enable random access in the timeline and to enable rendering the animation to image files. Now we're going to render a volume in Arnold, but first we need to talk some more about file caches. I've saved this exercise file with the file cache node set to pass-through mode so that the scene will open correctly for you. But if you want to reliably render a simulation sequence, a disk cache needs to exist first. I cannot include the cache files with the exercise files because it's too much data to distribute over the internet. And so you'll need to generate the cache like I have here. We saw how to do that in the previous movie. In the file cache node parameters, we see that there's an absolute path to a Bifrost object sequence. But in this case, this is the path to the folder on my hard drive. With the current version of Bifrost, there is no way to automatically make cached simulations portable. This is actually a headache for us right now. If you saved out a cache in the last movie, then you'll need to paste in the path to your files here. If you don't have a cache, you can write one now. A disk cache isn't required for rendering the first frame of this simulation. However, for testing materials and lighting, you'll need to inspect representative frames throughout the simulation, which in turn means that you need a disk cache. Once you have a disk cache created and correctly referenced here, then you can set the mode to read mode. And because my graph is currently paused, nothing happens in the viewport. Now I'm ready to assign an AI standard volume. So let's open up the Hypershade window. In the Hypershade menus, choose Create, Arnold Shader Volume, AI Standard Volume. The AI Standard Volume node is created. You can select it and press the F key to frame it. And we need to drag it over into the Bifrost graph. So with the middle mouse button, drag that AI Standard Volume node over into the Bifrost graph, and it creates a material reference. And we want to wire this up just as we saw previously in the chapter. We need an Assign Material node. So click on the Bifrost graph, press the Tab key, and start typing in MATER, and we'll find Assign Material. We want to connect the AI Standard Volume material reference to the volume material input. Connect the file cache first object port to the geometry input, and take the output of that assigned material and plug it into the output of the graph. So we've assigned an AI standard volume material with default parameters. So let's see what that looks like. We can minimize the hypershade and unpause the graph. We can use the keyboard shortcut, which is Control period. And that'll take a moment, but when we look in our viewport here, we don't see anything change. And although we have assigned the material correctly, the parameters for that material are not correct. We'll need to go back to the hypershade, back to the property editor. The AI standard volume has an attribute editor preset to plug in the correct values for these various attributes so that it will render in Arnold. Click and hold on the presets button and choose Default Bifrost Aero Replace. And as soon as you do that, now we see something in our viewport. The important part of that process was that the density channel was set correctly. It needs to be set to voxel fog density in order to find the density of the Bifrost Aero object. We can see what this looks like if we do an Arnold render. So I'll minimize some of these windows here. And in the camera view, we can choose Renderer Arnold. And we can start the interactive production rendering. That'll take a moment to initialize, but once it does, we see we've got a volumetric shader applied onto that Bifrost object. We can stop the interactive production rendering and replace that default material with one that I've created. So let's open these windows again. I got these minimized. Back in the hypershade, I've provided a shader network, Cloud AIST Vol. So middle mouse drag that over into the Bifrost graph. And then we want to connect that instead of this default standard volume. So just plug that into the volume material. We don't need this AI standard volume node anymore, so we can just delete that. Now let's see what this material looks like. Minimize these windows again. And I actually want to go to frame 1 of the simulation, and that's because it takes a while for the fog to build up in density. So I'll go to frame 1. Once that updates, then I can start the interactive production rendering once again. And here's the rendering with the cloud shader that I created. There's just one more thing that we'll want to do to optimize our rendering and to prevent any possible errors. I'll stop the interactive production rendering. And I want to go back to the Bifrost graph and insert a node here right before the output. And that's going to set the Arnold volume settings. So click in the graph and press the Tab key and start typing in SET. We're looking for Set Arnold Volume Settings. Create that node and wire it up. Take the output of the assigned material node, plug it into Set Arnold Volume Settings volume input. Take the out volume output and plug it into the out geometry port on the Bifrost graph output. Select the Set Arnold Volume Settings node, and we want to change a couple of parameters here. Step size determines the volumetric sampling, and lower values will give us better quality, but will take longer to render. A step size value of 0 is automatic. I've experimented with this already, and I've decided that a step size value of 2 hits the sweet spot between render quality and render time. Also, just as a safety, I want to increase the volume padding. I'm not seeing any render errors currently, but in pre-production for this course, I did encounter some issues, and it may be resolution dependent. If you render at a different frame size, you may see render issues when you didn't see them at a different frame size. I'll set the volume padding to a value of 10. Increasing the volume padding extends the boundary of the volumetric shape a little bit to prevent any possibility of render errors. With those changes made, we can minimize the graph. We want to reinitialize this view here, so we'll rewind back to frame 0 and then step forward to frame 1. Once that updates, we can resume the interactive production rendering. We may not notice any dramatic difference in the rendering, but increasing the step size will improve the render times. And increasing the volume padding will prevent any errors where the volume actually doesn't render in certain areas. That's how to render a volume in Arnold. In this brief introduction to the Bifrost graph, we didn't have time to delve deeply into 3D programming techniques. Hopefully I'll be able to cover some of that in a subsequent course. Meanwhile, if you want to learn more about Bifrost, I recommend the Autodesk Area website. Currently, if you go to the Tutorials section, you won't see a category for Bifrost. But you can go to the search engine and type in Bifrost, and then click Tutorials to filter the results. Once you start building your own graphs, if you run into any issues or have any questions, you can go to the Bifrost forum. Just go to Forums, Bifrost. And since Bifrost is an open framework, it's easy to share and modify tools. The Area website hosts Bifrost graphs and compounds submitted by users and Autodesk developers. Just go to Downloads, and then over on the left, click on Bifrost. And then you can download all of those shared tools. I hope you've accomplished your learning goals with this course, and thanks for watching. Now go forth and build super cool stuff in Bifrost.